Hello everyone, my name is Francisco Gil Couri. I am a professor at Federal University of São Carlos, Brazil, and today I'll be talking about strength, deformation behavior, and other properties of chrome cobalt nickel alloys, acryatomic and non-acryatomic. Unfortunately, due to COVID restrictions, I am not able to travel to the conference, so Diego Santana, who is a PhD student that works with me, will be giving this talk in my behalf. So the work shown here is based on extensive literature review we performed, and also a significant amount of work that us and a large team that I present here on this slide have been working on. So it's other faculty from Federal University of São Carlos, other universities that helped a lot on all this work, and graduate and students and undergraduate students. So just to give a short introduction, we all know that one of the biggest potentials of high entropy alloys is especially the almost infinite number of compositions that we can design. And some of these compositions, and it's important to say that only some of these compositions do display very good combinations of properties. And chrome cobalt nickel alloys are one of these alloys that have been discovered, that are being studied, that do display very good combinations of properties. So just to give a brief history outline on these alloy developments, by looking at the number of publications per year, we can identify that the study of chrome cobalt nickel alloys, which is the orange line here, really spiked after 2016. So at 2014, these compositions were produced by Vu. I'm going to mention this study later. And then at 2016, Gludovat's really, after this paper by Gludovat's, it's probably one of the most cited papers on HEA literature, showed, among other things, this diagram that shows that chrome cobalt nickel are one of the toughest materials ever made among any material. So that's really when the publications on this field started to grow very, very quickly at a higher rate than, for example, other studies in high entropy alloys field as a whole. So just a brief overview of the phase equilibrium of the system. For chrome contents from 40 to 50%, we do display a large FCC single phase field, especially at high temperatures. By decreasing the temperature, we start seeing the chrome-rich phases, which are the BCC and sigma. Sigma is more on the chrome cobalt side. They start to, the phase field, they are stable grow. And at even lower temperatures on the cobalt chrome side, HCP phase forms. So this HCP phase is discontinuous. It's present for almost pure cobalt and for cobalt chrome alloys. And the FCC phase decomposes into a 2 FCC phase at some temperature. So this is due to magnetic effects, and this, to our knowledge, this part of the phase diagram has not been explored too much in the sense of mechanical properties. So this is an area that people have not performed a lot of studies on. So moving on to strength and deformation of these alloys, I'm going to start talking about tensile properties. And one thing that these alloys do show really promising results is grain refinement strengthening. So on the acryatomic chrome cobalt nickel alloys, we know at least 3 studies have been done to identify the Howe patch constants, so the effect of grain refinement on the yield strength, and they diverge. The studies give some reasons for that based on concentration impurity, and we're going to talk a little bit more about this on the very last slide of this presentation. And on the non-acryatomic composition, also some studies have been performed. I'm giving here an example of a higher chrome alloy, and I'm going to talk a lot in this presentation about higher chrome-containing alloys. And basically summarizing these results on this table, what we see is by increasing chrome, we get a higher intrinsic yield strength, the sigma 0 term, and also higher Howe patch grain refinement constants. So this is very interesting and points to the direction of having higher chrome contents being something interesting. So we can see here an alloy without chrome has a very small sigma 0 and a relatively small Howe patch grain refinement constant. And when we go to the acryatomic composition, both these constants go up, and then when we go up to this alloy that have even higher amounts of chrome, both these constants go up. I'm going to come back on the sigma 0 term soon, but this shows that these chrome cobalt nickel alloys not only are intrinsically strong, but they also can benefit greatly from grain refinement. So studies on techniques and alloying additions to help further increase grain refinement are welcome on this area. And regarding solid solution strengthening, so the sigma zero term, that trend I just showed can be well explained by Vervan's model. So this is Wu's work that I mentioned on that was the first study to really report these compositions. They show that chrome cobalt nickel alloys are stronger and do display a better ductility than other Cantor alloy derived equiatomic compositions, as shown on these two curves. And basically what Vervan's model shows, that is probably the most widely used solid solution strengthening model for high entropy alloys, is that there are two things that really control the yield strength of these FCC materials: the shear modulus and the atomic size or the atomic volume mismatch. So the bigger these two terms, the higher the strength. And this term is especially varies a lot from alloy to alloy. And what we show here is that the shear modulus chrome is the element that apparently increases the most the shear modulus, but even more important, when we have chromium, that is the biggest atom on this system, when we mix it with chrome and with cobalt and nickel, we get very large delta V here, which is the atomic volumetric mismatch. So this is better shown in this picture here. So here we have 50 nickel, 50 cobalt, and here we have chrome, and this end is manganese. But we're really interested in this line. What we see is when we go from nickel, cobalt, and we start increasing the chrome content, the predicted strength by Vervan's model shows that it goes up to about 50% chrome. We cannot get there because the FCC single phase field ends before that, but we can get to 45%, for example, of chrome. And this trend shows us that when we go from 25 chrome to 33, which is the equiatomic composition, to 45, the yield strength should go up. And that's what we observe here. When we look at when we produce these alloys experimentally, they're all FCC, we see that trend experimentally. So higher chrome contents is increasing the solid solution strengthening via atomic size mismatch mainly. And this is also well shown by this study that we performed on a diffusion multiple. So this is basically a compositionally graded sample that we have on this end here cobalt nickel, on this end here iron manganese, and down here chrome. So we can clearly see that the highest entropy region does not match at all with the hardest region. So this is all single phase FCC. And we see that the strongest region is really when we go from cobalt nickel to chrome, as shown by Vervan's model. So in this figure here, we basically took EDS data from the whole area and applied Vervan's model, and we can see that it explains very well the experimental data. So we really think using these type of predictive models is a very strong way to develop new alloys. I'm not going to talk in this presentation a lot about precipitation strengthening. I would invite everyone to watch Diego Santana's talk. I'm going to move on to deformation mechanism. That's another very interesting topic of these alloys. So by changing compositions, we can go from dislocation glide only to TWIP effect and trip effect. So this figure was plotted using this empirical equation for stacking fault energy proposed by Gustavo Bertoli, and by fitting about 20 experimental data points of stacking fault energy. And what we basically observe, all these dots here are experimental alloys, that the trend seems to follow more or less what we see for steels. So when the stacking fault energy is between 15 and 45, we tend to see a lot of TWIP. This does not mean that it's TWIP exclusive, but what we call here TWIP dominated, when we see a lot of deformation twinning. And when we go to a lower stacking fault energy of 15 and below, we start having much more TRIP, so transformation to the HCP phase. This is also well shown by DFT calculations. So this similar trend is observed for the intrinsic stacking fault energy. This paper derives relations for other stacking fault energies. I recommend reading for more details. And the reason why I'm saying that these alloys are not TWIP exclusive is, for example, it has been shown that for the equiatomic composition, we do have a fraction of HCP phase forming. It seems to not be very large since it's hard to detect by X-ray diffraction. It's always very refined, and it is well shown by HRTM, but conventional TM and XRD techniques have trouble detecting this HCP form. So that's why we call these alloys TWIP dominated and not TWIP exclusive. And when we go to the lower stacking fault energies, for example, this one, which is 40 chrome, 40 cobalt, 30 nickel, then we do observe HCP fractions, much larger HCP fractions and thicker plates observable by conventional TEM and selected area diffraction pattern. And the effect we expect these deformation mechanisms have on these alloys is similar to what we see on TWIP steels, for example, or TRIP steels. Here, for example, is an in situ study on this composition, which is TRIP. And basically, what we're doing is doing the tensile test with synchrotron X-ray diffraction. And what we're seeing is when we have the TRIP onset, the work hardening rate stops decreasing. So this, thinking about Considere's criterion, will postpone the uniform elongation instability point to higher strengths, making the alloy more ductile. So more studies are always necessary to show particularities of this system, but this is the general explanation. Just one comment on short-range ordering. This is probably the most controversial topic for these alloys right now. There are some great studies showing experimental evidence of short-range ordering and effects this will have on mechanical properties and the dislocation structure of the alloy. And there are other great studies also showing that without evoking short-range ordering, most of the literature results can already be explained. So more studies in this area are being performed and are welcome, since this is a very open topic right now. And one particular area of interest is the discussion of how local atomic environments impact dislocation motion and the separation of partials, of dislocation partials. So moving on, one very important thing we should note here is that looking at the tensile properties alone of these alloys would hardly justify any application. And the reason we say that is because if we compare the tensile stress strain curve of these alloys with, for example, some austenitic high manganese steels or some austenitic or gamma nickel superalloys such as Inconel 625, we see that these alloys are good, but would hardly justify the high cost, especially due to the high cobalt contents. So we really need to look beyond tensile properties alone to justify their application. And one of the first that is really what has attracted most people is toughness. So the Glutovac paper I already mentioned shows this very well via fracture toughness CTOD measurements, and they show that these alloys have very large and very impressive fracture toughness that goes up when we go to cryogenic temperatures. It's interesting to see that with impact testing, with Sharpie impact testing, that the strain rate is much larger. The absorbed energy goes down as temperature goes down. So they do a nice discussion of this, so the trend is somewhat inverse, but nonetheless, the absorbed energy is very high, typically larger than what you see for conventional materials and also other HEAs. So the toughness of these alloys is very, very large. Another thing that should be mentioned here is corrosion resistance, and these alloys do display outstanding corrosion resistance on synthetic seawater. So by doing potential dynamic polarization and impedance tests, we show that especially when you go to alloys that are richer in chrome, we do observe a great increase in the corrosion resistance. So all these parameters here we selected to compare different alloys. We show that, for example, the alloy with 45% chrome is better than the equiatomic alloy and better than an alloy with lower chrome content. And most of these alloys, especially the ones with higher chrome, are better than Inconel 625 and stainless steel. So this alloy, the Inconel, is a benchmark alloy for corrosion resistance, and these alloys are much better in terms of corrosion resistance than Inconel. And what's also very interesting is when we cold work, when we put some cold work 40% rolling deformation on them, we see that some of these corrosion parameters go up. So this alloy displays a great corrosion resistance in an annealed and cold work condition, which is very interesting. So this is an area where these alloys really excel. So combination of toughness and corrosion resistance. It's one area that could justify it. It's much better than, for example, nickel superalloys, and it's an area that could justify applying these alloys. There are multiple studies on other properties. I'm not going to go in details. I invite you to read a review paper we recently published. Just a summary, these other properties, these alloys do not underperform than most nickel superalloys and steels, wear oxidation, fatigue. So it's always similar or better, basically, on those properties, of course. One final remark I'd like to make is regarding processability. One thing we think it's very critical is to report the content of interstitial on these alloys, and we show this on this curve that basically shows the nitrogen concentration on a melt at 1550 degrees Celsius of nitrogen versus the partial pressure of nitrogen and chrome content. Basically what this is showing is when we increase the chrome content, the nitrogen solubility spikes up orders of magnitudes on the melt. So, for example, if we're testing on air or in a poor vacuum atmosphere, an alloy that has more than 30% chrome would be on this region right here. So the melt will incorporate a lot of nitrogen. And nitrogen is very soluble on these alloys on the FCC phase. It has been shown in the literature. So a lot of these works that are being published that are not reporting the nitrogen content might have different levels of nitrogen, and that could really impact all the properties we've seen today. So one important takeaway, in our opinion, from this is that reporting nitrogen, especially nitrogen content on these alloys, should be very important. So I'm not going to read the conclusions here for the sake of time, just a summary of what we talked. I would like to thank our funding agencies and the other institutions we're collaborating with, Colorado School of Mines, Universidade de Lisboa, ANU, Unesp, and UFMG, and also PanDat and Computherm for providing licenses for this work. Thank you very much. Please send any questions you have.